we've spent some time talking about continuity on open intervals, but let's talk a little bit about it on closed intervals. So if I have a function and it's defined on a closed interval AB, so that just means that it includes the endpoints. But let's say it's defined everywhere, even including the endpoints. And let's assume we know it's continuous on an open interval. Let's say we've already done the legwork and said, all right, we know it's continuous inside the interval, but what about at the endpoints? Well, if we can then show that the limit as it approaches the left boundary from the right is equal to that function value, again, it's got to be defined. And if we can show that its limit as it approaches the right boundary from the left is equal to the value at that right boundary, then we can say that it's continuous on the closed interval. So we can extend the idea of continuity into the closed interval. And an interesting tidbit here is that if it's continuous on a closed interval that's also bounded, so let's say A and B are both not some sort of infinity, then we can say that f is actually uniformly continuous as well, which is a very strong result that's used in maths that are a little bit beyond here, but just a little taste. So knowing that, let's talk about this f of x equals the square root of 1 minus x squared. And that's the semicircle for the unit circle. It's the top half of the unit circle. So the first one is f defined on some closed interval? Well, in this case, it's defined all the way from -1 to 1. So that tells me my interval is -1 to 1. And we know it's defined there. Now, is it continuous in the open interval? Well, yes. And we could do a little bit of work there if we wanted to show that. But generally speaking, it's going to be continuous because any value that you plug in for the limit, it's defined there. You're not seeing any gaps or anything like that. So we're going to say it's continuous on -1 to 1. The third one is the limit as it approaches from the right equal to the function value? Well, in this case, f of -1 is 0, f of +1 is 0. So the limit, as you go this way, is it actually 0? So if I plug in -1, am I going to get some sort of strange behavior versus when I plug in the limit? And the answer is no. So as it approaches -1 from the right, it equals the function value. As it approaches +1 from the left, it's equal to the function value. Now, we did use a little bit of hand waving here. It really comes down to this. We know that the square root is a continuous function on, I don't know why I have 1 infinity there. That should be 0 infinity. We know the square root function is continuous, and we can show that. There's any number of ways we can show that, but let's not do that right now. And there's a second piece. If I have some composite function, f of g of x, and we do have that, because what we have is a square root of 1 minus x squared. So that's a composed function. Then what we can do is we can pass the limit through. Instead of being the limit of f of g, we can say it's f of the limit for g. So what we're really doing is instead of doing the square root, we can pass the limit in, and the limit of 1 minus x squared, or the limit is anything for 1 minus x squared, is easy to define, right? That's well understood. We just plug it in. So since we know that the square root's continuous, and we have this result from f being continuous, we can kind of hand wave and kind of cheat our way through this. So, that actually needs to go here. So what we find is, based upon all of that information, f is continuous on -1, 1.